Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 17. It's on dipole forces. Before we talk about dipole forces, we should probably identify what a dipole is. Water is a great example of one. We have one oxygen and two hydrogens, and since oxygen is highly electronegative, it's going to pull the electrons towards it. And so it's going to have partial positive charges where the hydrogen is and partial negative charges where the oxygen is. And so it's a dipole. What does that mean? If we ever have separation between the positive and negative charges, we've created a dipole from the positive to the negative. And so dipole forces are going to usually occur when we have at least one polar molecule. And so that's called a dipole. It's going to have partial charges, positive and negative. And so we can have a dipole force between a dipole and a dipole. So it's called a dipole-dipole force. We can use diagrams to figure out how they're going to orient themselves, and the most famous one is called hydrogen bonds. Hydrogen bonds are going to form when we have hydrogen bonded to either oxygen, nitrogen, or fluorine, and it creates a dipole. It's going to hold molecules together. We could also have an attraction between a dipole and an induced dipole. This is something that's not polar but can be for just a second. The strength of this force between the two is going to be based on the polarizability, in other words, how much we can make that turn into a dipole, and then the magnitude of the original dipole. And then finally, we can have a force between a dipole and an ion. This is going to be really important when we're using dipoles to break down solutions. An example would be water breaking down salt. And so before we get into dipoles, make sure you understand the difference between intermolecular and intramolecular. Intermolecular is going to be between molecules, like interstate goes between states. And so the force between this one molecule of hydrochloric acid and this one is going to be an intermolecular. Intramolecular is going to be the covalent bond between the chlorine and the hydrogen. Likewise, we could have water around salt. They're going to have an ionic bond between the chlorine and the sodium ions, but it would be an intermolecular between the water and the ions themselves. Also, this helps explain the difference between real and ideal gases. Remember, ideal gases are just theoretical, but as the gases become closer to a liquid, as they start to condense, we're going to start to have attractive forces, and some of these are going to be dipole forces. So let's look at a specific dipole. Let's say we have hydrochloric acid. Hydrochloric acid is going to have one atom of hydrogen and one of chlorine. Chlorine is going to pull that electron towards itself, and so it's going to have a partial positive and negative charge. Positive is going to be where the hydrogen is. Negative is going to be where the chlorine is. And so if we have two of these, what we'll get is a dipole-dipole force. It's simply a force between the two dipoles, and it's going to hold hydrochloric acid together. So if I had a bunch of hydrochloric acid molecules and I put them like this, they could never exist like this, but let's say I put them like that, with all their negatives on the inside and positives on the outside, how do you think they would orient themselves? Well, it would be something like this. They're going to orient themselves so we have a negative to a positive to a negative to a positive to a negative to a positive. So imagine in hydrochloric acid we have all these interconnections going on. Now, a specific type of dipole is going to be a hydrogen bond. Hydrogen bonds are going to occur. Lots of people think it's between hydrogen and something else. It's not that. So a hydrogen bond is going to occur when we have hydrogen bonded to either a nitrogen, oxygen, or a fluorine. And so in water, we have hydrogen bonded to oxygen. So when it does that, we're going to have unequal sharing, and so we're going to have a dipole. We're going to have negative side where the oxygen is and a positive side where the hydrogen is. Now let me show you where the hydrogen bond is. This is how water would really orient itself. This is going to be a hydrogen bond right here between the hydrogen and the oxygen of an adjacent molecule, or between this hydrogen and this oxygen of this adjacent molecule. And hydrogen bonds are incredibly important, and they allow small molecules like water to have pretty good bonds that hold them together. In fact, that's why it's really hard to change the temperature of water. It has a high specific heat. It's due to these hydrogen bonds. But we could find it in larger molecules as well. So if we're looking at the nitrogenous bases, these are the bases on the inside of DNA, this ladder. What's holding them together are going to be these hydrogen bonds. Hydrogen bonds are holding it. It's between the hydrogen and oxygen, or hydrogen and nitrogen of another molecule. And so hydrogen bonds are incredibly important. But again, they're dipole-dipole. We could also have a dipole-induced dipole force. Okay, what's this going to be? It's going to be between a polar molecule and something that has no charge at all. What's something that has no charge? And noble gas is an example of that. So let's say we have hydrochloric acid molecule next to argon. Argon, remember, is going to have no charge. All the electrons are equally distributed. Well, as it comes closer, watch what happens as argon approaches hydrochloric acid. some of those electrons on its surface are going to be attracted towards this positive charge of the hydrogen. And as a result, what we're going to create is a temporary dipole or an instantaneous dipole. So it just happens for a fraction in time, but now we have this force holding them together, a force between the dipole and an induced dipole. Now, what's going to increase the ability to be induced? Well, it's going to be the strength of this dipole. The more strength there is in that polarity, the more likely we are to induce dipoles. And then the other thing is going to be the polarizability of that other atom or other molecule. The more electrons it has, the more likely those electrons can be tugged on, and we can make these instantaneous dipoles. And then finally, we could have an attraction between a dipole and an ion. And so a great example of this is how water dissolves salt. There are going to be huge bonds intermolecular between the chloride and the sodium ions, and that's why salt has this beautiful crystalline structure. But you know, if we add it to water, we can quickly break it down and can form a solution. Well, what's going on there? We have a chlorine ion, and then we have a sodium ion, and what's going to happen is the water will orient like this around that chloride ion. And so we're going to have the positive ends of the water attracted to the negative ends of the ion. If we look at the sodium, we're going to have the negative parts of the water attracted to the positive parts of the sodium. And so what they're really doing is kind of ushering these ions away from that original ionic compound. What happens if we remove the water? Then those ionic compounds come back again and we get that sodium chloride. So did you learn the following? That we could relate the real gas behavior to some of these intermolecular? Remember, as a gas gets closer to condensation, we're going to have more of these attractive intermolecular forces. Did you learn to relate the feature of a polar molecule to the attraction between them? Remember, this diagram shows that. We've got two dipoles, and you could probably turn it so you could orient it the correct way. And then finally, could we use Coulomb's law to explain why dipoles are attracted to ions? Remember, all it has to do is those partial charges of the dipole, in this case water, are attracted to the ionic charges, or the ions, and so that's going to allow them to dissolve it. And it's simply Coulomb's law, that attraction between positive and negative, and I hope that was helpful.